Guys, on today's tech tip, we're going to talk about exhaust back pressure on a turbocharged application. We're going to go over how to monitor back pressure, why you want to monitor back pressure, and the effects it has on your engine. Back pressure is one of those things that I'd say only a small percentage of the current racing community really kind of monitors and understands. And back pressure has a few different terms throughout the industry. Exhaust back pressure is one. It's abbreviated down to EBP or EMAP, which EMAP is basically exhaust manifold pressure, as you're used to hearing MAP, which is manifold pressure. Essentially, they're all the same terms, all measuring the same thing. It's the pressure, the actual physical pressure in your exhaust system after the exhaust leaves the engine and then gets to the turbocharger. Exhaust back pressure varies depending on your engine combination pretty greatly. So the things that are going to come into play with exhaust back pressure are going to be the engine size, cam profile comes into this also, but mainly where you're going to get into it is the end of the road, which is your turbo exhaust housing. So depending on if you have a single turbo combination or a twin turbo combination, all of the exhaust from your engine must go through your turbine housing. Now this is a single turbo setup that we run on a Toro Mustang. It's an 88 millimeter with a 1.2 T6 housing. So all of the exhaust from the engine, again, has to go through all the way down to the smallest section of this snail. Which if you ever looked at a turbo very close, it's a very narrow pathway there. And then into the turbine wheel, and then to exit the exhaust where then it gets free again. Turbochargers are designed like this because it's trying to compress the exhaust energy, compress the heat, and then allow it to expand in the turbine housing and then expand in your downpipe to get. So it creates a pressure to spin the turbine because that's how the turbocharger turns a compressor to make horsepower, and then it exits there. The problem with this system is now we're creating this huge restriction for the exhaust and your engine can't breathe properly. So we need to find the balance between the engine breathing properly and turning the turbocharger fast enough. Back pressure is an important thing to monitor so you can view how much pressure is actually in your exhaust. Now, if we were working on a naturally aspirated engine or a supercharger engine, we wouldn't even be talking about this because your exhaust is going to be open and it's going to be free to the atmosphere and your engine is going to be free basically from the port of the head out, and the exhaust is allowed to escape. As the piston comes up and tries to force the exhaust out, when there's back pressure present from your turbocharger system, now the piston has to push that burnt exhaust gas past that pressure. So it's actually physically harder for the engine to pump that used air out of the exhaust system. So what this is doing is it's robbing horsepower. Now, this is a necessary evil in a turbocharged application because we need the turbo to create horsepower, but what we want to do is find the balance between the engine's efficiency and the turbocharger's efficiency so we don't actually lose horsepower to try to make horsepower. When we're balancing our turbo system to our car, there's a lot of things that come into play. The first of all is going to be the rule set. If this is a race car and you're racing a rule set that limits you to one turbocharger, you're not going to be able to change this. So basically the back pressure that you're going to experience is what you have to deal with. You're going to measure it and monitor it to see how bad it is, at what boost level you start crossing over, and then at that point maybe limit the power or see what else you can do to try to free that up to get more efficiency from the engine. If you have no rule set, you can put as big a turbocharger as you want on there with the biggest turbine. You can put twin turbos on there, so now you have two turbine housings for the exhaust to exit, one on each side. This is all going to free up back pressure to allow the engine to run at its natural efficiency state. But now we come into the problem of spooling the turbo. So now we're in the next balance to get as large of a turbo as we can on the car to your engine combination to be able to spool the turbo, to be able to leave the starting line, and to be able to make a maximum amount of boost in a short period of time. There's a lot of different options when it comes to turbochargers, and I feel like every turbocharger company kind of has a different opinion on what they want the pressure ratio to be, what they want the back pressure to be on their turbocharger. I've heard people say that a 1-to-1 pressure ratio is fine, 2-to-1, even up to 3-to-1. So, you know, this is going to vary. Talk to your turbo manufacturer, talk to your engine builder, and try to find out where your combination needs to live for the maximum amount of power, the maximum amount of efficiency. Coming from our experience and simple physics of the engine, we know that zero back pressure is the best case scenario for the engine to be as efficient as possible. We can't achieve that on a turbo application. You wouldn't want that on a turbo application, but we're going to shoot for a 1-to-1 back pressure ratio. back pressure, EMAP, EBP, the pressure that's physically present in your exhaust system. Okay, you can use this tool, this value, for a lot of different things. So basically, what we're going to be measuring is the pressure in the exhaust system. What that's going to tell us is how efficient our turbo setup is compared to the boost level that we're running and the manifold pressure. We use this raw data value, the actual pressure number from the exhaust that we're reading on our pressure sensor, to calculate a pressure ratio. You've heard the term, oh, it can be 1-to-1 or 2-to-1. What that 1-to-1 or 2-to-1 is the pressure ratio. The pressure ratio is the ratio between the pressure in the exhaust side of the engine to the pressure of the intake side of the engine. So if our turbo is making 30 pounds of boost, we have 30 pounds of boost in our manifold on our map sensor, and our exhaust is making 30 pounds of pressure. We're reading 30 pounds on our back pressure sensor. We have a 1-to-1 ratio. So the pressure is equal between the exhaust system and the turbo system. Now we're running a single turbo. We start increasing the manifold pressure. Say we go up to 40 pounds of boost. You've noticed on your CO2 controller that you now have to add 5 pounds of CO2 to get 1 pound of boost, or 10 pounds of CO2 to get 3 pounds of boost. What's happening now is your pressure ratio is crossing over, and the pressure on the exhaust side is getting higher than the intake side. So now we have 40 pounds of boost in our manifold. We've got the boost controller turned up. We close the gate. Now, if we look at our back pressure sensor, we see that we have 80 pounds of pressure in our exhaust. So now we're up to a 2-to-1 ratio. The reason this happens is because the turbocharger sizing, the housing of the turbocharger and the turbine of the turbocharger is actually a little too small for that engine's requirement of airflow for 40 pounds of boost. So what's happening is you're going to have to overspeed the turbo. There's not enough physical room for the exhaust to get out and get by this turbine wheel to make that much manifold pressure in a 1-to-1 state. So the pressure ratio is calculated from the pressure in the exhaust to the intake manifold. You heard we just refer to it as a 1-to-1 pressure or 2-to-1 pressure. Some people also can refer to it as a percentage. So if you have a 100% pressure ratio, that's 1-to-1. If you have 120%, now you're 1.2-to-1. So there's a couple different terms depending on your ECU or your tuner or your engine builder they want to use. They all mean the same thing. It's just the unit of measure for that application. So again, we have the pressure in the exhaust to the pressure in the intake. So now I'm going to talk a little bit about why back pressure on the engine cuts down on the efficiency of the engine, cuts down on the horsepower, and makes the engine actually harder to run and harder to make horsepower, and essentially isn't as good for the engine as you may ideally want it to be. So imagine we have 40 pounds of boost in our manifold pressure, we have 80 pounds of boost in our exhaust system. So now we are at a 2-to-1 or 200% pressure ratio from exhaust to intake. So now when that pressure that you're reading in your exhaust system, that's a constant pressure. So that's from the cylinder head to the turbocharger because it's filled that whole system, and that's the pressure that you have now on the back of your valve through your exhaust port. That pressure is 80 pounds. So now we imagine the piston coming up, trying to force out the burnt exhaust. And remember, the piston's coming up just from pressure from the other side. It doesn't actually have any power on its own cylinder driving it up there. So now it's trying to push that burnt exhaust past the exhaust valve, through the exhaust system, get it out of the engine so we can have the next power stroke. Now, with 80 pounds of pressure holding back on this valve, the valve is open, there's 80 pounds of pressure on this side of the system. Now the piston is trying to push up this burnt exhaust pass through 80 pounds. What's happening is all of the exhaust now isn't exiting the cylinder, and some of that heat and burnt exhaust gas is staying in that cylinder when the valve shuts. So as you can imagine, that's going to cut down on your horsepower potential no matter how much manifold your pressure you're making on there. And if you've dynoed a car from a low manifold pressure to a high manifold pressure, you've probably seen this in your dyno numbers. So you're running it 10 pounds, 20 pounds, 30 pounds, everyone's excited, man, we're making 40 pounds, 40 horsepower per pound of boost. Now you start to get up to the 40 pound boost range or 35 pound boost range, and you start cutting back, man, we're only making 20 horsepower per pound of boost, and now we're making 10 horsepower per pound of boost. What you're experiencing is losing efficiency from the engine's natural state, and that's why you're not making as much horsepower per pound of boost that you're making, because the back pressure is now so high in that engine. If you have a back pressure sensor, you'll be able to monitor that and kind of get to a tipping point. You'll get to a ratio where you see your performances start dropping off, and then you'll kind of know where that is for your engine and for your turbo combination, so then you can make the decision, do I put a larger turbine on it? Do I need more horsepower? And you can start to tune your turbo system and tune your turbo kit around your back pressure which is the value that you're going to want to look at more than your manifold pressure. Because what comes along with this high back pressure is high heat. Remember, pressure makes heat on its own, but now we have, a 1300 degree exhaust gas, add 80 pounds of pressure, that's adding temperature. This whole exhaust system is now glowing red because we have a 200% pressure ratio, and that air is still in your engine instead of getting out of your engine. So your next combustion, your next intake stroke, the air that's coming in is now mixing with this hot air and becoming even hotter to cause detonation in just a poor running engine. Another thing that you may have experienced with adding a turbocharger to an engine, if you put a turbo on a stock engine, you run it, you're doing good, you get up 20 pounds of boost, and now you have valve float. Oh, I need valve springs. Well, the reason for that is because your stock spring wasn't rated for a turbocharged engine. It was rated for a naturally aspirated engine. And the reason because of that is because now we've added pressure to the backside of the valve. So if this spring, when the valve is open and the spring is trying to close the valve, we now have 20, 30, 40 pounds of pressure per square inch, depending on the valve size, on the head of the valve, and the spring has to overcome that to close. So you're actually fighting the spring. On a lot of high pressure ratio factory OE engines, you'll see that they actually come with a heavier spring on the exhaust side. A lot of aftermarket applications, they do the same thing. So talk to your engine builder when you're speccing out cams and valve springs for your car to what turbo you're going to run and what exhaust pressure you're going to run on that. Actually comes into role here on what valve spring you need, what valve material you need, and what kind of cam profile you need. So again, the back pressure is a tool that can be used all the way around your engine combo to get the most efficiency out of your combination. We can add boost and make power easy, but if we free up horsepower that's already there, your engine's going to live better, it's going to last longer, your parts are going to live better, and you're going to have a better experience racing your car. I mentioned a second ago valve material. The valve material comes into play with the spring on the back pressure because of what I said before is that the pressure makes heat. You have high combustion temps, now you have an excessively high pressure on your exhaust side, and that's on the valve head the whole time. This heat now is being transferred in the valve. So if we have a stainless valve, that's going to be better than the factory alloy, we're doing good. Now we move, now our valves are starting to tool up, they're starting to beat up the face because these valves are now turning into a molten material where it's softer and it's going to form more into the seat and it's going to try to pull the valve head off. If you have ever worked on any small displacement engines or Honda engines, single turbo is a must. A smaller turbo is a must because you have to, again, spool this turbo. So you're going to run into a high pressure ratio situation most of the time. And that's why 90% of these engines are running Inconel valves or titanium valves, at least on the exhaust side, to manage that heat so the metal doesn't lose its form because of the extra heat created by back pressure. So if you're having valve train issues, back pressure is another good tool to know why, we have excessive heat on our valve because my turbocharger is too small. Well, let me just go to a larger housing and see if it gets any better, try to save the life of the engine some. Where do you put your back pressure sensor? This is a question that comes up all the time, and if you haven't used one before, it's a great question because there are some do's and don'ts when it comes to this, and there are better locations to put it. I've seen, your first indication is like, let me just drill the turbo housing and tap it and put my fitting right there because I don't need to take the turbo kit apart. I can get right at it, maybe add it on, while your car is already together. This is not a good idea because of the heat and the material of the housing itself. If it's a cast stainless or just a cast iron, and because all of the heat is trapped in the turbine housing, this gets extremely hot. I've witnessed this, I've experienced this plenty of times. What happens is the fitting threads actually fail or the fitting breaks because of the vibration in the line, and pretty much guaranteed that it's not going to end well. You could weld a fitting to this. Again, it's not the best case because depending on the fitting style, a lot of times it will still just break because of the heat that's in such a small component and the vibration it picks up from the engine and the line. So I wouldn't recommend drilling, tapping, or welding it into your housing yourself. But basically, we want it to be between the exhaust collector and the turbo inlet. If we have a twin turbo setup, it's pretty straightforward. We have this header, this side of the engine, pipe goes right into the turbo. We could put our sensor anywhere along that pipe and it's going to measure the same amount of pressure. We want it after the collector because, obviously all the cylinders come together here, so we don't want to just pick up one cylinder. We want it out here where the pressure is trying to equalize and pick it up there the most. When it's time to place the bung in your exhaust pipe, you may have some limitations here depending on the packaging of your car. But one of the do's and don'ts is basically you don't want it on the bottom of this exhaust pipe, right? This is a pipe off of my car. This header is actually off my car. You can see my port here is basically in a 12 o'clock position. The reason I do that is because a methanol car or ethanol car, and even some gasoline cars, they create a lot of moisture in the exhaust, especially on cold start. What's going to happen is all that moisture is going to settle to the bottom, and it's going to go in your line, fill your canister, and just sit on the sensor. It's okay, the sensors can, have water in them. We can use pressure sensors on cooling systems and things like that, but remember, this is exhaust water. It's not very good. It's going to cause a lot of corrosion. It's just going to cause issues in your system. So you want to have this mounted upwards the best you can, just so, again, water can drain back from the sensor, and it will just help the corrosion factor in your lines and everything moving forward. So as we talked about before, this is a twin turbo application. So we have our exhaust header and our merge pipe to our turbocharger, and we have just our sensor in line to that. It's going to read perfectly. In a single turbo application, you're going to have a merge pipe. This is a merge off El Toro. So on a system like this, we're going to want to go ahead and get our bung somewhere in the merge of the two sides. You can put it in one side. Naturally, this is equalizing some, but you could have a little crossover or not exactly even pressure. So I would recommend always putting it into the merge below the flange somewhere to be able to pick up equal from both sides. Here at RIFE, we offer a back pressure monitoring kit, or you can buy the pieces separately depending on if you already have a sensor or a sensor block, or you want to make your own line. But we have it pretty simplified where you can order it all together. What it's going to come with is the canister. Canister has a 90-degree mount. I'll open this up in a second. Hardware to mount the mount. It's going to come with a stainless steel line, a weld-in bung, and a thread-in bung with 2 compression fittings to connect the line from your exhaust system to the canister. Now you can trim this line down depending on how long you need to make it, and you can also loop this line, and we'll talk about that here in a second. So what we get is a canister, sensor, and a line. When it comes to sensor selection, a 100 psi sensor is going to meet most of the requirements of domestic engines racing, because that's going to, again, get you 100 psi. So even if you're at a 2-to-1 pressure ratio, that'd be 50 pounds of boost to 100 pounds. You step this up to a 150 if you feel like you need to, but the sensor resolution on 100 psi is a good choice. We'll go ahead and open this package up so you can take a look at the canister and the mount. So here is our RIFE back pressure canister. This is a billet aluminum piece that's been anodized to protect against corrosion. The inside of this canister is filled with a stainless steel mesh. On the inlet and the exit of the canister, there's actually a screen. In case the mesh breaks down, it doesn't go back into your exhaust system or into your sensor. We haven't experienced this, but we put that there as a nice safety item to protect against that. The canister itself does not have an inlet or an exit. It's just a dumb canister. It can be installed either way, depending on either direction. Come in from the exhaust here, sensor here, just however you want it. You think looks the best on your car, or however you fit it. Comes with a stainless steel bracket, so you can mount it in any location you want. The bracket is clockable anywhere on the top. It is round, so it doesn't really matter where it goes, or you can make your own bracket off. It's no big deal. On the canister, like we talked about having the fitting at the top of the exhaust pipe so water doesn't collect, we want to mount our canister in a orientation that if the water can drain back from it. So you don't want to mount this down below your header with your sensor on it here, because this is going to collect with moisture and pretty much have a water pressure reading at that point, which may not be that accurate. So we want to get this guy higher than your exhaust pipe so the water can drain back. If we can get it on an angle, if we can mount it vertical, then we're doing even better, just for longevity of the system and an accurate reading. As I said, it doesn't have an inlet and an exit. The sensor can go on either side. It is okay to screw the sensor directly onto the canister. It's totally fine, works out great. Or if you have one of the RIFE remote sensor blocks like I run on my car, I actually have an AN line coming from the canister to the sensor block. So we have our stainless steel line feeding the sensor block, and then you can use a soft Teflon AN line like a normal brake line, or if you're making your own lines, to the sensor block, because the temperature after the canister is cool enough to run into the block. While we're talking about temperature, that is one of the reasons why you need a canister. So the canisters are designed for 2 reasons. One reason, the stainless steel mesh absorbs the heat coming from your exhaust, because again, we have 1200 to 1600 degree exhaust depending on your application, and we don't want to damage our pressure sensor with that high heat, so we're going to need to cool it down. So we're doing that in 2 ways. One way, the stainless steel tube. The second way, the canister itself. The other purpose of the canister is to dampen the exhaust pulses. So it is a pressure dampener, which is acting as a mechanical filter for your data. As your engine fires, your firing order is inconsistent. So you're getting exhaust pulses on each cylinder at each different time. If it's twin turbo, now you have coming from the other side. If we had a sensor directly on our collector, you would actually pick up each exhaust pulse and your data would be very spiked. It would just look jagged like saw teeth, and you wouldn't have a very consistent, accurate reading. You could filter it electronically, but now you're slowing down your data, and that's not in real time and it's not accurate. So the mechanical filter is the proper use for this. Again, it's cooling it. It is buffering and dampening down the pulses from the exhaust to give you a steady reading for your ECU system. As far as the stainless steel line goes, I recommend trying to keep the line the length that we send it or trimming a few inches off of it. Again, this is to eliminate the heat from the exhaust air that's inside this tube getting to our sensor. If you're trying to mount this kind of close to the exhaust, maybe you've seen before loops in these lines. All these loops are doing is basically giving time for that exhaust to cool off through the loop system. I have a loop line off my car here. This is giving it time to cool down because the exhaust is going through the loops. Pretty simple. Some people like the loops, some people don't like the loops. Again, it doesn't really matter. You can do it either way. You're going to have a successful trip. Okay, so that was our brief rundown on exhaust back pressure and the effects of it. Hopefully you learned something. If you have any questions, please leave a comment below or reach out to us at rifesensors.com.